We asked him to take the final
Are there any questions before we get started? Okay. So the last lecture we reviewed complex numbers. And we learned this very important identity, which is this identity over here. Okay? And there are two ways you can write a complex number. You can either write a complex number this way, which is called a Cartesian form. You can write it in terms of maybe a magnitude of c due to the j theta, where theta is arctan of b over a. Okay, so this is called a Cartesian form. This is called a polar form. And one thing I'd like to remind you of is that this theta has always to be expressed in terms of radian. Okay, theta is in radian. When you want to use this kind of formula. So when you say something is 30 degrees, what you actually means is that 1 degree is equal to pi over 180 radians. 180 degrees is equal to pi radian. Okay, so you have to be mindful of that. So when you say e to the j 30 degrees, you actually mean that you convert this 30 degrees into radians before you plug into this kind of formula. Okay, that's something I'd like you to be aware of. Always express everything in terms of radians before you apply those formulas. Okay, so today I'd like to talk about resistor combinations and how do we do parallel and series connections. So if you have a voltage source, and if we connect this voltage source to resistors, R1, R2 for instance, and if there's a current I that flows in this circuit, and then you can quite easily see that V1 and V2 are equal to this. V1 is equal to I times R1. And the current that flows through R1 is the same as the current that flows to R2. So V2 is I times R2. But you know that the total V around this loop due to Kirchhoff voltage law is that this must be equal to V1 plus V2. And hence this must be equal to I R1 plus I R2. And then you group these two together, you see that you can also write V is equal to I R1 plus R2. And hence, this circuit can also be replaced by a consolidated circuit where this circuit has a series connection of the two resistors R1 plus R2. So if you write the KVL for that circuit, you get exactly this equation. If you write the KVL for this circuit, you get that equation. That is called connecting two resistors in series. Series connection. So if you have a number of resistors, say you connect them in series in this manner, then you can go through Kirchhoff voltage law, connect them to a voltage source, and show that this is equal to one resistor, Rs, where Rs equals to R1 plus R2 plus R3 plus R4. Okay, that is called series connection. And similarly, you can apply Kirchhoff current law and get another formula. This is gotten by Kirchhoff voltage law. and that if you have a current source having a current of I, for instance, and if you connect this current source to two resistors, R1, R2, and you can see that the voltage drop across these two resistors must be both V. Okay, V across this resistor and V across this resistor because they share the same voltage drop. So the current through resistor 1, I1, is different from the current through resistor 2, I2. So with Kirchhoff's current law, you can see that V must be I1, R1, but it also must be equal to I2, R2. Okay, V is the same, but then you know that by Kirchhoff's current law, I must be equal to I1 plus I2. Because the current that comes in here is I, the current that flows in here is I2, and the one that flows down that node is I2. So this must be true. And if this is the case, then you can see that I1 is equal to V over R1. From this equation, I2 is V over R2. Okay, so you can see that I can write I as being equal to V times 1 over R1 plus 1 over R2. Okay, and this is as if this is I, this is equal to V times 1 over Rp. Okay, where Rp is equal to 1 over R1, 1 over Rp is equal to 1 over R1 plus 1 over R2. So if you replace this with that, this looks like a circuit that is connected as such. And this is the current there, and this is an Rp. And if Rp takes this value, okay, the same current would flow in this circuit over here. This is called a parallel connection. So in general, if you have many resistors connected in parallel, and if you were to ask what the resistance is when they're connected in parallel, okay, the Rp that you see in this node here is 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So do you know how to connect resistors in parallel and resistors in series now? Are there any questions regarding this? Okay. So if there are no questions regarding this, let's move on. Yes? Are there any questions? No? Okay, so in general, Rp is equal to 1 over R1 plus R2 plus 1 over R3 plus 1 over R4. And this number can go on and on, depending on how many resistors you have. Okay, I make a mistake. I call this the geometric mean, and Aditya corrected me and said that this should be called the harmonic mean. Okay, I actually have another mistake to correct. The term volt is associated with Alessandro Volta, not Voltaire. Okay, this is an Italian physicist, but Voltaire is a French philosopher. Okay, so they're two different persons. So Volt is associated with Volta, and he's an Italian, living around 1800. Okay. Are there any other questions? If not, then let's move on and see what we can do with series connection. Other things that you can do with series connection is to use them as a voltage divider. We say one use of a resistor is that it can be used to mitigate the strength of a voltage source. Say you have a very high voltage source, maybe 100 volts here. 100 volts, and it's too high to connect your device. to this voltage source. You will get fried. Okay? So one thing you can do is to connect your device using what is known as the voltage divider. Okay, you connect your device to this voltage instead of that voltage. And you can figure out what voltage across the device would be if you connect to it using this terminal, because there would be a current flowing through this thing. The first voltage drop is equal to IR1. The second voltage drop is, what should be the second voltage drop across the second section? What should, R2, very good. It should IR2. And then I know that by the Kirchhoff voltage law, that the total voltage drop is equal to IR1 plus IR2, and hence this is equal to so if I were to look at this, VD over V, okay, it will be equal to IR2, okay, which is VD divided by IR1 plus R2. So the voltage of the device is R2 over R1 plus R2 times the voltage source. So this is called the voltage divider, because by this design, by this very design, you can adjust the voltage drop that should be occurring across the device. You can pick your R1 and R2. The larger you pick R2, the more voltage drop you have across the device, and the smaller you make R2, the less the voltage drop you can have across this device. So this is the voltage divider. And in general, if you have a very complicated circuit, the voltage source such as this one, and you have a whole bunch of resistors, 4 of them say, you can n of them if you want to, and if I call them R1, R2, R3, R4, and you can go through the similar analysis and figure out what the voltage should be across one of this resistor, okay? And you probably know that V across that resistor 2 should be equal to, proportional to R2 divided by the sum of resistors in the circuit. V. Okay, this is the voltage coming from the voltage source, and then it's divided by this ratio, yes?
If there are multiple voltage sources or like other resistors like in parallel or just like all over the circuit, do we need to find the entire circuit's equivalent resistance and the entire like voltage source?
Right, you need to simplify that circuit first before you reach this point. We'll talk about how to simplify that circuit. If you have parallel connections together with series connections, you simplify those circuits until you reach this point and then figure out the voltage divider formula. And then you have a current divider, which is by the same token as this picture over here. Say if I have a current source, I, R1, R2, and if I want to figure out the current going through I2, okay, it will be proportional to the ratio. I2 is equal to, let's call this I1, the ratio of 1 over R2 divided by the sum times I. Okay, you can work this out, and if you work out I2 and I from this formula, you will find that this formula is true. Now let me work that out for you. Okay. So I can actually, I is equal to that, and then I2 is equal to V over R2 according to this formula. Okay, so if I use this formula for V again, then I should have 1 over R2 times I divided by 1 over R1 plus 1 over R2 inverse. I use this formula for V again. Okay, I get this. This is I over here. And then I get the formula that this is 1 over R2 divided by 1 over R1 plus 1 over R2 times I. Okay, just as expected. Okay, I can just work the circuit out. And this is called a current divider. In general, if you have many parallel connections, then you can apply the current divider formula very much like you do to the voltage divider, but apply the reciprocal of the resistance every time. So a general current divider formula, say if I want to figure out the current through R3, okay, it is 1 over R3 divided by the sum of 1 over R1 plus R2 plus R3 plus 1 over R4 times the total current I. Okay, this is the current divider formula. Of course, you can simplify, but this ratio is reminiscent of this ratio. Whenever you see R replaced by 1 over R, whenever you see V replaced by I, okay, you get this current divider formula. Okay, are there any questions so far? So you can use this kind of circuit to route currents of different amount to different parts of the branches of the circuit. Okay, these are the use of a current and voltage divider. So given any complicated looking circuit, you can always use this kind of knowledge to simplify the circuit first. You can use parallel connections and series connections to consolidate the resistors into one and try to make your circuit as simple as possible. Let's see if we have some examples. Say if I have a circuit such as this one given in the textbook, R1, R2, and then I have an R0 over here. I have a voltage source over here. And then I have two resistors connected as such. These are called RA and RB. I can reduce this to a simpler circuit. Okay, first I find a series connection of this. RS. And then I can still maintain this branch if I want to. R0. And then I can find a parallel connection of this. So what is RS that I should put in here to make the two circuits equivalent to each other? R1 plus R2. Okay, very good. Many of you are getting it. And what is this R parallel here? 1 over? 1 over R1 plus 1 over R2. Okay, you just use that formula. What? Yeah, A and B, you're right. It should be A and B. Okay, thank you for pointing that out. So you have this thing, and then you have a simpler circuit to work with, and it should be a lot simpler than before. And then you can also connect these two in parallel. Apply that formula. And then write this formula as, or this circuit as R0, and then there should be just one resistor left. Okay, let me call this resistor R parallel. Okay, R parallel. And R parallel should be equal to 1 over the parallel connection of this one and that one over here. It should be 1 over RS plus 1 over RP. Okay, so if you do that connection, do this simplification, then you have only a circuit with one resistor, and then what further simplification can you do? You can consolidate these two. Okay, consolidate that two, and then have R final is equal to R0 plus R parallel. Okay, and then it becomes a really simple circuit to solve. You can solve for the current I very easily through this circuit. Are there any questions so far? What you can do with parallel and series connection, and what you can do to simplify circuits that you might have. Okay. So the next thing I'd like to talk about is source transformation. Source transformation so we have two kinds of sources. One being a voltage source. Let's say that this is my voltage source. Okay? And the other one being a current source. And the current source will look something like this. Sorry. It will look something like this. And then let's call this RS prime to begin with. We don't know if RS prime should be RS. And to a person outside, you really do not know whether you have a voltage source nor a current source if you only have access to these two terminals. If I tell you this is a black box, okay, put this inside a black box, then you only have access to these two terminals. How could I tell them apart? I can do experiments to tell them apart. One thing I can do is to hook a resistor here. And change this is the symbol for a variable resistor. I can change the value of my resistor gradually. I can change it from 0 value to infinite value and see how much current I can draw from this source. Okay? I can also do another experiment to this. I hook this to a variable resistor and change my resistor. Okay, this is called variable resistor. And see how much current I can draw from the second source. So we expect two things. We expect that the current, as a function of the resistor I hook onto, okay, to have two values. It will be at its maximum when RL is 0, but it will be at its minimum when RL is infinite. Okay, so it probably goes something like this. It goes to 0 when RL goes to infinity, but it will be at its maximum when RL is 0. And so if I set RL is equal to 0, what is the value of this current over here? The current when RL is 0 is equal to
V over
very good, V over RS. Okay, of course the minimum current is 0 when I make the resistor infinitely large. The second experiment I do the same. Okay, I make the resistor equal to 0. I should expect a maximum current to flow. But what is the current that I should have when I make RL equal to 0? It should be the value of this current source, right? So I would have something very similar. I would have this being equal to I. When I make a short circuit and make the resistor value equal to 0. And when I make RL infinite, let me call this IL, okay? IL, to denote the fact that this is the current flowing into the load. So if I make RL infinite, what will be the current flowing through RL in the bottom picture? If I make RL very, very large,
0.
is 0. So these two pictures are indistinguishable to a person trying to figure out what kind of sources I have. Okay. In order to make the two currents equal, you notice that the short circuit current have to be the same. This is called the short circuit current. I short circuit or short circuit current. In order to make the two currents the same for both of them, okay, I have to make my RS the same as, I have to make my V over RS to be the same as I. Okay, if I make this to be the same as I, if I make V over RS to be the same as I, then the two currents will be the same here. Okay, if I make V over RS to be the same as the I in this one, when I short circuit this one, the two currents will be the same. Okay, this is when you're trying to do an experiment to find how much current you can draw from this circuit. Another one is how much voltage you can gain out of them. In that case, you will try to make the voltage here as large as possible, and that is the case when you have an open circuit or when you have a resistor over here. So when you have infinite resistance over here, what is the voltage over here in this terminal? From what you have just learned, V open circuit will be equal to what when RL tends to infinity? Equal to V, okay, or V source. So the open circuit voltage for this is equal to V, okay? And also the same thing over here. If I were to make this equal to an infinite resistor and want to see the same voltage as the other circuit over here, what should RS prime be? If I force this to be infinitely large, all the current will go through this branch over here. Okay? And the voltage drop should be equal to I RS prime. So these two have to be the same. Okay, I better make sure that this is equal to V. So in order to make this two circuits equivalent to each other, RS prime must be equal to V over I. Okay? And then, in order to make the short circuit current to be the same, the short circuit current for this is I. The short circuit current for this is equal to V over RS. Okay? So from this I can see that this must be equal to I. And if I look at this formula and this formula over here, okay, RS prime must be equal to RS. If I compare that formula, if you compare these two formulas, okay, you can see that RS prime must be equal to RS in order for them to be behaving the same. So this circuit over here is indistinguishable from this circuit over here as you change this resistor out here. They will have the same short circuit current, the same open circuit voltage. Yes?
So will the two graphs have the same slope? Exactly?
Exactly. Yeah, you can go through the calculations. You don't believe me, you go through the calculation, you can see that in fact exactly have the same slope. Okay? And these are called the equivalent sources that you can have. You can express the voltage source in terms of a current source, and you can express a current source in terms of a voltage source using this model over here. So what we have then is that if RS prime is made to be the same as RS, they behave the same. Okay? So I always had a problem remembering their names. Okay? So this is called the Thevenin equivalent. This is called the Norton equivalent. Okay, this is Thevenin equivalent source. This is Norton. You can always transform a source from one to the other. Okay, given one source, you can always change it to the other one. And how I can use as a memory aid is that this is a series connection. Okay, this is a series connection. So S is closer to T. Okay, this is a parallel connection. So P is closer to N. Okay, so just don't get confused by the two names. You can use this as a memory aid. So the one that is in series connection is called Thevenin equivalent. The one that is in parallel connection is called Norton equivalent. Okay. So if I have something like this, I can change this problem too. I can change this problem to another problem because this is exactly the same as this one. And this is R source. This is exactly the same as R source. Okay. And what should I plug in here? How do I find the Norton equivalent of that thing over there? What kind of current should I put? What is I? I should be the short circuit current of the sources, right? The short circuit current is V over R naught. If you short out this thing over here, the current that flows is a short circuit current. And this source over here should be the short circuit current. So it should be V naught over R naught. Okay, so that's how you can reduce that problem over to that problem. And sometimes people like to take parallel connections. Okay, sometimes people like to calculate series connections. Okay, of course we like to calculate series connections more than we like parallel connections. But just in case you like to do parallel connections, you can convert this problem to this problem and do parallel connection. And you can have the same answer in both cases. Okay? So let's move on to do something else. So you know how to reduce problems, you know how to transform sources. You can transform a current source to a voltage source and vice versa. You know how to use parallel connections and series connections to consolidate resistors. Make it into one element if you want to. So given a very complicated circuit, you try to do reduction and make things simpler. So, but in general, when we have a very complicated circuit, the textbook teaches you a systematic manner, a systematic way to solve a very complicated problem, and that is called a node voltage method. I'm going to talk about what a node voltage method is. Okay, this method combines with KCL. Okay, so if you have a complicated circuit like this one over here, I do it by example. This source is 2 amps, and then it has a network that looks something like this. You have 3 volts over there. Okay, in the node voltage method, what you do first is to assign a voltage to every node. Okay, step 1, node voltage assignment. Okay, so I would call this voltage here V1. This is 1 node, this is 2 node, this is 3 node. Okay. And then the next thing you should do is to apply KCL at every node. And then solve equations. So let's apply the node voltage method to this very simple circuit over here. And actually we don't have to solve for V3. V3 is automatically known. If this is grounded, say this is grounded to be 0. So what is V3?
3.
V3 is exactly equal to 3, and we don't have to do anything. Okay, it's a piece of cake to solve it. Then we can write the current through each resistor. This is 2 ohms given in the textbook. This is 1 ohm, and then this is 4 ohm. Okay, so we can write the current through node 1. Say node 1 would have the current coming in, and the current leaving that. Okay, the current coming in is 2 amps. The current leaving this one is equal to V1 minus V2 divided by this resistor, which is 2. So this is KCL at node 1. And then you apply KCL at node 2. So node 2 you would have 0 current, say, coming in. Say if I were to compute all the currents that come in or leaving it, okay, I can compute the total current that are leaving it. Then I have the first piece of current that is leaving it is V2 minus V1 over 2. Okay? And then the second piece of current that is flowing downward like this is V2 minus 0. This is 0 volt. Okay, this is grounded. V2 minus 0 over 4. And the third piece of current that is flowing that way is equal to V2 minus V3 over 1. Okay, this is KCL on the second node.